All right, class, welcome to section 5.2, rational functions. So as we discussed in the last section, in this chapter, we'll be tackling rational functions and radical functions. And here is a rational function. So a rational function is simply a ratio between two polynomials, okay? And I know this might look a little scary, but when we discussed polynomials in the last chapter, I showed you how we define polynomials, how we do not want to hold on to A, B, C for coefficients because we don't know what the highest degree or what the highest power, in other words, is going to be. And so again, as you see here, there are two polynomial functions or two polynomials. The degrees are different, some kind of letters, P and Q, whatever they might be. So I'm just going to show you what a rational function looks like, right? There could be two quadratics that are divided. It could be, as we look later on, here it is a linear and a quadratic, maybe a cubic, but not really. Well, this one's a cubic, but it's all nicely factored out for you. Okay, so that's what a rational function is, just two polynomials divided into each other. So again, rational because it's a ratio, all right? So the basic parent functions, the toolkit functions that we discussed back in chapter 1 for any rational function are 1 over x. So let me graph this one for you, remind you. We also call this the reciprocal function. So if you remember maybe from 1.3, it was a funny looking broken graph. So in other words, whatever graphs we're going to do next for this section, for any rational function, they will very much resemble this graph right here. And then the 1 over x squared, I'm going to graph this one also for you, and then we'll look at some specific features. And then 1 over x squared also was in your library of functions. And the difference between 1 over x and 1 over x squared is that 1 over x squared is going to be just on the positive side of the y-axis, right? Okay, so couple things as you see, and we discussed this in chapter 1 as well. We talked about the domain of each one of these kind of functions, and we talked about the domain specifically of any rational function. And as you see, and here I'll write it for you in two different ways. This would be the set builder notation. So the domain, of course, is all the values of x that I'm allowed to plug in to this function in order to produce a real number answer. And so the domain of a rational function, or 1 over x or 1 over x squared, specifically is we want to make sure that the denominator of either one of these fractions is never going to equal to 0. So of course what makes x 0 is x of 0, right? So of course we also wrote this negative infinity up to 0, including and then union 0 to infinity. So as you see, by putting parentheses at both ends of 0, that means 0 is not included in this interval or in this interval. Okay. So it also, as you see, this graph jumps over the y-axis, right? So there is no point on this graph where x would equal to 0. Okay, we're jumping over the y-axis. There is no y-axis intercept. And the same thing for 1 over x squared. And because x cannot equal to 0, the y value is never going to equal to 0, specifically for these functions, because 1 divided by a non-zero number is not going to equal to 0. So as you see, we're also jumping with the graph over the x-axis, so there are no x-axis intercepts in either one of them. Okay. However, one thing you will also notice is that when we jump over the x or the y axis, the graph gets super, super close to it. We're going to call these lines asymptotes. So an asymptote is a line that a graph gets super, super close to, but it's not going to touch it. So one more time, the difference between just the 1 over x and the 1 over x squared is because, again, you're squaring the x value. So whether you plug in a negative or a positive, x squared is going to turn out positive, and 1 divided by a positive number, of course, is just a positive. Okay, so that's why the graph is going to have both sides on the positive side of the y-axis. Okay. All right, so let's look at all the features that a rational function is going to have as we discuss a specific function. So as we're looking at these rational functions, again, factoring is going to be very important, and I will make sure that the examples we're dealing with will all be factorable. So here it is. I'm going to factor this quadratic at the top, and of course numbers that multiply to 3 and add to before are 3 and 1. Factoring the denominator, the 2x squared at the front is a 2x and an x. Again, numbers that multiply to 3 or 3 and 1. I'm going to put a minus here and a plus here. So if you check, you're going to get the 1x minus 6x, which equals to the negative 5x in the middle. So in other words, we factored correctly. Okay. All right, so here are going to be the steps in getting the graph of that rational function. So number one, what is the domain? The domain is going to be all real numbers except for, and so we have to make sure that the denominator never equals to 0, which is why it's so nice to have this denominator factored out. So when is this denominator going to be 0? Well, the solutions for it would be 3. So we have to exclude 3 out of the domain. And then the other value that's going to make the denominator 0 is negative 1/2. So again, these are values that are excluded. You can write this also in set builder notation, so make sure x does not equal to 3, because you actually do not want the denominator to be 0. And x should not equal to negative 1/2, right? You could write it in interval notation, but that's just going to be too much, so don't worry about it. I think all real numbers except 4 is the easiest way to write this domain. Okay, so make sure the x is not going to be 3 or negative 1/2, because you don't want the bottom to be 0. So it turns out that we are going to skip over these values, sometimes with vertical asymptotes and sometimes with holes. And what's the difference? So first things first, the vertical asymptote of a graph is simply a vertical line where the graph gets towards positive and negative infinity. So in other words, the graph gets up to positive infinity or down to negative infinity. So don't worry about these notations. It simply means that the graph gets closer and closer to these vertical lines, but they're not going to touch it. Okay. So how do we find them? It says right here that the vertical asymptote of a rational function will occur wherever the denominator of the function is equal to 0 and the numerator is not 0. So if I look at this rational function right here, where is the denominator equal to 0? So in other words, at all those places, I'm going to get a vertical asymptote. So instead of writing so much, I'm going to write VA for vertical asymptote. So I'm going to get a vertical asymptote at x equals to negative 1/2, because that's where the denominator of the fraction is going to be equal to 0, but the numerator is not 0. So we will skip over this vertical line. X cannot equal to negative 1/2. I'll show you how the graph will look like, and we're just going to jump over it. All right, for x equals to 3, if you notice, x equals to 3 is a value where both numerator and the denominator are equal to 0. So a hole occurs in the graph if an input causes both the numerator and denominator to be 0. Okay, so if that happens, then we're going to get a hole in the graph at x equals to 3. So we have to exclude that value out of our graph, but we're going to exclude it with a little tiny pixel missing out of the graph with a little hole. Okay. All right, and we're going to move on. We'll put all this information together in our graph in a bit. The next thing that we need that these graphs are going to have is not just vertical asymptotes. This is a vertical asymptote right here. It's a vertical line that the graph gets super close to. But as you see, we also have horizontal asymptotes. How do we find these? So the horizontal asymptote of a rational function can be determined by looking at the degrees of numerator and the denominator. If the degree of the numerator is less than the degree of the denominator, then you will have a horizontal asymptote at y equals to 0. So you look at the degree of the top versus the degree of the bottom. So I'm going to take this function that I've given you above, and I'm going to bring it closer to us. Just copying it over. And then I had the 2x squared minus 5x and minus 3. So we're looking at the degree of the numerator versus the degree of the denominator. So as we see, the degrees, so in other words, the highest exponent, they are the same. Okay. Now, it says if the degree of the numerator equals to the degree of the denominator, that's the case we're in, then we're going to have a horizontal asymptote at y equals to the leading coefficient, the ratio of the leading coefficients. The leading coefficient at the top is 1. The leading coefficient at the bottom is 2. So we're going to have a horizontal asymptote at y equals to 1/2. Okay. Now it also says if the degree of the numerator happens to be exactly 1 more than the degree of the denominator, we're going to get a slant asymptote. So in other words, it's not vertical, it's not horizontal, it's slanted. Okay, so a slanted asymptote is sideways, right? So the slope of that line is not going to be 0 and is not going to be undefined, right? It's just the slanted line. And that slanted asymptote is just the quotient of that division. I didn't really give you any problems like this. So it's there, but I'm not going to ask you on problems with slant asymptotes. Okay. Now, intercepts are easy. We've been finding intercepts for graphs since the beginning. So these are the two values that we always like to find. In other words, to find the intercepts, we do what? Make x0 find the y, make y0 find the x. So again, these are easy points to find on the graph. So here it is. Let me go back. Here's the function that we're still discussing. So one more time, plug in 0 for x, see what you're going to get. Well, it's going to be 0 squared minus 4 times 0 plus 3 over 2 times 0 squared minus 5 times 0 minus 3. So, of course, everything except for the constant term happens to go away. So you get a -1 for an answer. Okay. Now, if you make y equal to 0, so the function equal to 0, then what do you get? The thing is, in a fraction, as we already discussed, the denominator can never equal to 0. That makes the fraction undefined. So if I make a fraction equal to 0, the only thing that can be 0 in this fraction is the numerator. And so we already factored out that top. Excuse me. And so we get our answer to be x equals to 1. Now, of course, the other answer is x equals to 3. But remember how we said from the beginning that the domain of our function is cannot yet have x is equal to 3. As a matter of fact, once we took that out of the domain, we could indeed go and reduce this fraction. Okay, so take the x minus 3 completely out of this function. But again, you need to make sure still before you reduce them to say that x cannot equal to 3, because if x equals to 3, then you would be dividing out zeros, and you can't do that. Okay, because you can't divide by 0. So the only x-axis intercept that we're going to have, whoops, maybe delete a bit too much, is x equals to 1. Okay, so let's put all of this on the graph. First of all, here, I'm going to put the 2 points that we found. So the only crossing points through the axes are at x is 0, y is -1, or x equals to 1 and y is 0. So these are my only crossing points. Then what did we found? We found a horizontal asymptote that says y equals to 1/2. So I'm going to draw this horizontal line, y equals to 1/2, right here. So this is a line that the graph is going to get super close to. What else? I have a vertical asymptote at x equals to -1/2. So x equals to -1/2 is a vertical line that the graph is going to get super close to. Not going to touch it. Okay. And then, of course, I'm going to get a hole at x equals to 3. So keep that in mind as well. Okay. All right. So how am I going to fit this graph? I know that my graph is going to get close to these lines somehow, but we don't, all I have is 2 points, and I know that these lines guide my graph, so the graph's going to get close to them. Now keep in mind, this is what the graphs of these kind of functions look like, okay? So they get closer and closer to your vertical and horizontal asymptotes, yes? And they're not going to touch them. So here it is. The graph, in fact, is going to look like this. Now remember, at x equals to 3, you have to put a hole in the graph and go on. And then I'm going to go on this side, opposite, right, diagonally opposite to it. I'm mimicking the graph of the 1 over x function. And there it is. Now, how else could I be sure that this graph looks like this? Of course, we have graphing calculators, and I know I might have a whole bunch here. I'm going to clear this one. So if I remember correctly, in the numerator, I had an x squared. Oops. I'll try again. X squared minus 4x and plus 3 divided by, in the denominator, be sure in your graphing calculators that you group the numerator and the denominator. So 2x squared minus 5x and minus 3. Okay, so when I graph this function, exactly as I told you, we do see, and again, on your graphing calculator, you might not see this nice dotted line, this vertical asymptote. It does show up on this graphing calculator, though, so it's exactly as we said, right? Now, as a matter of fact, if you see, if I zoom in closer and closer, the graph is going to cross through -1 as we had it. The graph crosses through +1 as you had it, and you might not see it. Yep. It jumps right over, so I just want to see the hole in the graph. You might not see it. Oh, maybe. No. It's not gonna be visible because it's really just missing a tiny pixel. Let me see here. Table. Yeah. Values. Huh. You might see it on your graphing calculator. If you look at your table of values in your graphing calculator, I don't see it here for some reason. I don't know why. What's wrong with this one? Anyways, you should see undefined when x is equal to 3. So try your graphing calculator and see what happens. But there's a hole. There's just a tiny pixel missing. If you graph these with Desmos, Desmos will show you that little hole as you trace along the graph really nicely. Okay, so let's do more examples. And in your homework and on a test, I will take you through these steps. So first things first, I would ask you to find the domain. Now, to find the domain, either one of the problems you need to do factor as much as you can the numerator and the denominator. Okay. So again, here it is, numbers that multiply to 6 and add to be 5 are 2 and 3. Of course, these x minus 3's are going to reduce. But first things first, before you reduce them, the domain is going to be all real numbers except for 2 and 3. So you are not allowed to divide by 0. And this x minus 3 is there, and you cannot cross out zeros, divide by 0, so you have to exclude 2 and 3 from the domain. Now, it says you will have a vertical asymptote at any x value that makes the denominator 0 but not the numerator 0. And you will have a hole in the graph at any x value where x that makes the denominator and the numerator equals to 0. So if you want, you can reduce this. In fact, now that you did make sure to say that the function cannot include x equals to 3 in its domain, or that point where x is 3. So here it is. The next thing we're going to be looking at is horizontal asymptote. So it said if the degree of the top is less than the degree of the bottom, and the degree of the numerator is 0 because we don't have any x's whatsoever, but the degree of the denominator is 1, so top is less than the bottom, then y equals to 0 will be a horizontal asymptote. So if the degree of the top is less than the degree of the bottom, then y equals to 0 is a horizontal asymptote. In other words, the x-axis. That's what y equals to 0 is, the x-axis. And then the last thing to do is find the intercept. So again, make x 0, find y. So if I plug in 0 into this function, I'm just going to get, in whatever format of it you want to see, plug in a 0 right here. That makes all the x's equal to 0, so you get negative 3 over 6, which of course reduces to negative 1/2. It's exactly what you get if you plug in x equals to 0 in this format. Okay, so x is 0, you get 1 at the top and negative 2 at the bottom. And finally, if you make y equal to 0, now of course, as we said, if the only way a fraction is equal to 0 is if the top is 0, but the top can never equal to 0. So there is no x-axis intercept. And that's true because the x-axis is a horizontal asymptote. So let's put all of these things in the graph. So I have a vertical asymptote at x equals to 2. I have a horizontal asymptote at y equals to 0. That's basically my x-axis. I do not have any x-axis intercepts, but I do have a y-axis intercept at negative 2. Okay. So, and a hole in the graph at x equals to 3. So because the graph crosses down here, and again, you can put in your graphing calculator and look at it, but I am simply mimicking the y, the 1 over x graph. Yes, so it has to have this shape. And there it is. And by the way, even if you think at this graph right here, how does 1 over x and 1 over x minus 2 compare to each other? Well, this one has to be simply shifted 2 units to the right from 1 over x, and that's exactly what happened. We shifted the graph 2 units to the right. It's not centered at the y-axis, it's centered at x equals to 2. So again, if you think of transformations, that's exactly what we had. And then when you hit an x of 3, put a hole in the graph. Okay, so let's do this again. I have an x plus 1, and the bottom actually factors into an x minus 3 and a second x minus 3. So that's an x plus 1 over x minus 3 quantity squared. All right. So number 1, what's the domain? The domain is all real numbers except for 3. So the only thing that makes the bottom 0 is an x of 3. All right, we'll have a vertical asymptote at any x value that makes the denominator 0. It's excluded out of the domain, but also you don't have the numerator also equaling to 0. So this time we're not going to have a hole in the graph because we don't have a common factor in this problem to both numerator and denominator. So in other words, there is no x value that makes both the top and the bottom equal to 0. So we only have the bottom being 0 at x equals to 3, so we'll have a vertical asymptote there. Then we'll have a horizontal asymptote at y equals to 0 because, again, the degree of the top is 1, and that's less than the degree of the bottom, which is 2. And then intercepts make x equal to 0. So if you plug in a 0 for x, you're going to simply get 1 over 9. And if you make y equal to 0, again, the only thing that can be 0 in a fraction is the numerator. So the numerator is x plus 1. And it's going to equal to 0 if x is negative 1. So in other words, these are my two x and y axis intercepts. I have if x is 0, y is 1/9. If y is 0, x is negative 1. So here are my 2 points. Of crossing. 1/9 is super close to the origin, and then negative 1. Okay. What else do I have? I have a vertical asymptote at x equals to 3. And then I have a horizontal asymptote that says y equals to 0. So even though I do have a crossing point, you cannot cross a vertical asymptote, but you can cross a horizontal asymptote. So if this graph makes it a little, like, wait a minute, what am I supposed to do? Of course, if it sounds confusing, and even if not, let's put this in our graphing calculator to see what truly happens. So x plus 1, x plus 1, do that for every one of your functions, but especially if you get confused. And here it is. So let's graph this and see what happens. All right, so here it is. I do see my vertical asymptote of x equals to 3, yes. And I do see my crossing point. One is at 0, 1/9, and the other one, we said it was at negative 1, 0. Here it is. See, crossing at negative 1, 0 through the x-axis. So it looks like the graph is getting close, 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 but it kind of comes in, it dips a little bit, and then it goes up. So you couldn't quite find that turning point, again, as I keep saying, unless you go to calculus. But these are things that we already knew. The graph has to come, y equals to 0, so the x-axis is a horizontal asymptote, yes? But then the graph kind of dips, a bit, and then goes up and crosses and goes up. So you have to make the graph go up, and then it comes up here and just goes alongside the x-axis again. So ends and alongside the x-axis, and it's again going up towards positive infinity alongside this vertical asymptote of x equals to 3. So why is the difference? Why did we have both ends go the same way, but in this problem it's up and down? Of course, the reason for it is the fact that we were squaring the x minus 3. So our toolkit function is just really 1 over x squared. This is where both ends are on the same side because you're squaring that value, right? So both sides are going to go to positive infinity, versus if it's simple, 1 over x, as you see, the graph ends up on opposite sides of that vertical asymptote. Okay, so that's the difference. All right, let's try this again. It's actually not that bad. There's much to figure out. And as I said, I would give you the steps. Number 1, find me the domain. For this, all these problems, you should factor them out. So I have a 2x and an x. Numbers that multiply to 5. There aren't many options, but 5 and 1. And let's put a plus to 5 and negative to 1. So they multiply to negative 5. And then if you try for that middle term, you're going to get 5x minus 2x, which is the 3x in the middle. Now when I factor the denominator, numbers that multiply to 3 and subtract to be 2 are 3 and 1. And again, it should be a positive 3 and a negative 1. They add up to a positive 2, multiplied to a negative 1. So as you see, the domain, what we have to exclude out of the domain is values that make the denominator equal to 0. And they are positive 1 and negative 3. We will have a vertical asymptote at any x value that only makes the bottom 0, and that's negative 3. But of course, at x equals to 1, we're going to have a hole in the graph. Okay, so it gets reduced out, but with a hole. Okay. Horizontal asymptotes. Again, we're looking at the degree of the top versus the degree of the bottom. And when they are the same, then y equals to the leading coefficient at the top versus the leading coefficient at the bottom, which is a 1. So y equals to 2 is a horizontal asymptote. And the last step is make x equals 0, find y. Make y equals to 0, find x. So if I plug in a 0 for x, I'm going to get negative 5 at the top left and negative 3 at the bottom, so 5/3. And when I make y equal to 0, then the only thing that can be 0 again is the numerator. And when I solve this equation, I'm going to get that x is negative 5/2, or negative 2.5. It's not going to be x equals to 1 because remember, x cannot equal 1. That value had to be excluded out of the domain. Okay, so I have a horizontal asymptote at y equals to 2. I have a vertical asymptote at x equals to negative 3. I have crossing points at x is negative 2.5 and y is 0. And x is 0, y is 5/3. 5/3 is about 1.6, so here it is. Okay. So therefore, I immediately know my graph is going to be in this quadrant. It's as if these new vertical asymptotes shift my x and y axes from the graphs before. Okay. And then diagonally opposite, I'll have the other graph. And it said to make sure that x equals to 1, and there's a hole in the graph there. So that's it. And again, you're very welcome to put this in your graphing calculator and see that indeed it mimics this graph right here. Now, what your graphing calculator might not show is these dotted lines for your vertical and horizontal asymptotes, but that's exactly why we don't just use the graphing calculator, but this little bit of extra knowledge so that we can come up with a nice, pretty graph. Okay, and the hole in the graph, which we would otherwise not see. Okay. So one more time, domain is all real numbers except for whatever makes the bottom 0, which is -1 and 2. I have a vertical asymptote at any x value that only makes the bottom 0, but not the top. So as you see, there are no common factors to the numerator and the denominator. Horizontal asymptote, I have to think about their degrees. So, but something that we looked at back in chapter 4, when we were given the factors and we wanted that leading term. So just think about what you would get if you would multiply this out, but you don't need to multiply the whole thing. I only need the term at the front. So I'd get an x squared. But be very careful. Here I really have 3 parentheses. I have an x squared from this parentheses and then times another x. So there's really 3 parentheses there that give me an x to the 3rd at the bottom. So the fact that the degree of the top is less than the degree of the bottom, there's more x factors at the bottom than at the top, that means that y equals to 0 will be a horizontal asymptote. All right. And then find intercepts, make x equal to 0, find the y. So it's nice when it's not factored because you see the full-on polynomial, but then you have to know how to factor. So everything has its trade-off. This is going to take us a little longer, but not that much. So plug in a 0 for x. 0 plus 2 is 2. Times -3 is -6. 1 squared is 1. And 1 times -2 is -2. So that's going to be a 3. So I have 0, 3 as one of my intercepts. And now if y equals to 0, remember the only thing that can be 0 is the numerator. So then the 2 solutions here would be x equals to -2 and x equals to +3. All right, so let's put all of this in. Let's start with the intercept. Crossing at 0, 3, crossing at -2, 0, and 3, 0. So I make sure to hit these points. I have vertical asymptotes at x equals to -1. And x equals to +2. And I have a horizontal asymptote, funny, at y equals to 0. So in other words, it might be another one of those dipping things. So this graph is kind of funny. I'm not so sure how it's going to go, but I know I have to guide it through these 3 points and these 3 vertical and horizontal asymptotes. So I'm going to graph this for you because we have graphing calculators. So at the top, if I remember correctly, I had an x plus 2 times x minus 3. And let me make sure. Okay, I just want to put in an extra parentheses for the numerator. All right. So I have the whole numerator in a parentheses divided, and I need the whole denominator in another parentheses. And there I had an x minus 1, I believe, squared, times, I've already forgotten, let me make sure. Oh, plus 1, plus 2 minus 3. Plus 1 minus 2 plus 1. And then x minus 2. Okay. Yeah. All right. So here are my vertical asymptotes, horizontal asymptotes. As you see, the y-axis only kind of goes between -1 and 1, so I'm going to bring this back a bit. And then here is the graph in between there. Okay. I'm going to try and copy this nicely through here. So the graph comes down from down below and then dips in and goes up. Then from the same side it comes down and then goes up. And then it comes on this side, crosses, and then ends up alongside the y-axis, or the x-axis. Okay. All right, now, again, would this be correct? Look, at x equals to -1, see how the factor was being squared? This is why at -1, the graph is on both sides of the vertical asymptote at the same end. At x equals to 2, the graph is an opposite ends, right? Because that factor is linear, right? So it's kind of like the same as our polynomials. If a 0 is squared, then the graph bounces off to stay on the same side. If the factor is linear, then you have a sign change, so the graph goes on the other side of the x-axis. Okay, but again, graphing calculators are super helpful. So write an equation based on this graph. So it is definitely a rational function. And I'm going to look at, what do I see? I see a vertical asymptote at x equals to -1. That means x plus 1 is a factor for the denominator. Then I see another vertical asymptote at x equals to 2. So that means x minus 2 is a factor, again, of the denominator, makes the denominator 0. Now, x minus 2 is going to be squared because just as we discussed, the graph is going to end up on the same side of the vertical asymptote, right, on both sides of it. Whereas this one is on opposite ends, so therefore this factor is linear to the power of 1. Then, at any x-axis intercept produces a 0 for the numerator. So I have an x minus 1 factor in the numerator, right? However, how does the graph cross here at x equals to 1? It doesn't cross nicely linear as it would be in the next problem, but it crosses more just like a cubic function. So therefore, I'm going to put a power of 3 there, okay? Because it crosses cubic. Now, the other thing is that I see that y equals to 2 is a horizontal asymptote. Therefore, the numerator has a coefficient of 2 versus the denominator has a coefficient of 1 at the top to make y equal to 2 over 1, our horizontal asymptote, when the degrees, as you see, are the same. Okay. Now, one other way to do this problem is to use a y-axis intercept or another extra point. I'm not so sure for this one if 0, -1/2 might be it. So in other words, if you plug in 0 for x, you get a -1/2 for y. It doesn't quite, it could be. So you could try that way as well. But this is another way. Again, I just know that y equals to 2 has to come up to be a horizontal asymptote. So therefore, the coefficient at the top has to be 2 and the bottom has to be 1. Let's try this again. So any vertical asymptote means a factor for the denominator. So try that. Where are the vertical asymptotes? And again, they are at -3, so x plus 3 is a factor of the bottom. And again, it's linear. See how these are at opposite ends? And then I have another one at 3, but that x equals to 3, this has to be quadratic. I'm sorry, yeah, quadratic, the power of 2, because the graph ends at the same side. Okay. And then linear factors are only at, x-axis intercepts are only at 2. So therefore, x minus 2 is a factor of the numerator, and it goes in linearly. So like a line, therefore, I put a power of 1. Okay. And so this time I easily see the y-axis intercept is at x is 0, y is -2. So let's see if we can find an extra a value from it, like we did for our polynomials. So if I plug in a -2 for y and a 0 for x, that should get me the value for a. So I have that -2 equals to -2a, and the bottom I have a 3 times 9, which is 27. So cross multiply if you want, or multiply both sides by 27. Then divide by -2, so as you see, a itself is a 27. So I don't want to waste more time. I'm just going to come back and put it in. So there you go. That's what would make the graph go exactly through a 0, -2, even with all these other numbers up here. Okay. So let's try this again with, this time I'm not giving you the graph, but I'm saying to you what the graph will have. So write an equation of a rational function with a given characteristics. I have a vertical asymptote at x equals to -1. So therefore, x equals to -1 is a solution for the denominator. I have a double 0 at x equals to 2. So n means x minus 2 is a factor of the numerator, and double 0 means it's going to come to the power of 2. Okay. And then maybe I have an a value here, and that's all there is. Now again, no one says that this could not be squared. Doesn't tell me exactly how the graph ends, but we'll just leave it simple. So again, if you put a square, it wouldn't be wrong. We don't know where the graph ends on left and right, so it's a possible equation. Okay, so it doesn't have to be one possible answer only. The y-intercept is at 0, 2. So in other words, if we plug in a 0 for x and a 2 for y, then we should be able to find this a value. -2 squared is a +4. Divided by 1, it's still a +4. So 2 divided by 4, by the way, is a half. So I can write that y equals to 1/2 x minus 2 squared over x plus 1. You can write it doesn't look good if you write fractions over fractions, so 1/2 over 1 is just 1/2 like that. You can write a 0.5 if you want, if that makes you feel better. But it's not good to have just the 1/2 over something. It's just not pretty to have fractions inside fractions. All right, so let's try this one more time. I have vertical asymptotes, so therefore factors of the denominator at x equals to 2 and x equals to -3. I have a 0 at 0, 0. So in other words, x minus 0 is a solution. And to find the possible extra A value, it doesn't tell me anything about horizontal asymptotes, right? So I'm not quite sure what the degree of the top versus the degree of the bottom is supposed to look like, because they didn't bother us with a horizontal asymptote. But we know that passes through 1, 4. So plug in a 4 for y and plug in a 1 for x. So that should get us a possible A value. And that's a 1A, which is A, and negative 1 times positive 4 is negative 4. So therefore A is going to equal to negative 16, right? Negative 16 divided by negative 4 is a positive 4. In other words, to solve this equation here, I multiply both sides by negative 4. It's kind of like as we did with those rational equations in the last section. Yes, undo a division, we multiply both sides. So therefore here is finally my last function. You can write it as an f of x. You can write it as y equals. It means the same thing. So again, no one says you couldn't have squared one of them or both. Keep it simple. It didn't say anything about how the graph ends. Like this I can tell, right? Because the graph ends on the same side here. Therefore, that value has to be squared, and opposite ends here. Therefore, that value has to be to the power of 1 for a vertical asymptote. But since I am not given a graph, I don't know where that ends. So I just leave it as simple, a factor of 1. Yes. All right, this is it.